Hello, everyone. This class, we're going to continue with the computational methods in engineering, which is here, we're going to just carry on with the basic operations in MATLAB, right? So the introduction to MATLAB, just going over some basic calculations, operations. So to carry on from our last class introduction regarding variables, or the general operation of the matrices. So this class, we're going to focus a little bit more on a few examples with engineering backgrounds. So if we do a quick recap of our last class. So last class, we talked about the naming of the variables in MATLAB, right? So basically, we have to start with letter followed by numbers, or we can also use the underscore, right? So underscores, you can use multiple underscores, but the longest name of the variable is 63, right? You can only use 63 of these symbols. So basically, we showed different forms of the scale of the, I would say, the values for the variables. It can be scalars, which is recognized as 1-by-1 arrays, right, or 1-by-1 matrix, and then there can be 1-by-n or n-by-1 arrays, or n-by-n matrices, right? So we said that MATLAB actually uses matrices to do the calculations. And also we showed that there are differences regarding the operation, especially the multiplication and division of these matrices. If you want element by element calculations, which is the most of the scenario in this class or in a lot of the engineering calculations, then we will use the dot operators, the dot multiplications. And then we introduced the hierarchy of arithmetic operations, right? So we start from things in the parentheses, right? And then the exponential, and then the multiplication, division, and then summation or subtraction, okay? So also we show that the equal sign basically assign values to the variables. All right. So an array of numbers is a structural variable in the MATLAB within the one variable name. A set of numbers can be stored. Right. Basically, you can have the values existing as the array or the matrices. Array, vector, and matrix operations are efficient in MATLAB computations. Right. So we're going to realize that later on as we work more with the MATLAB software. Okay, so this class, we're going to focus on a little bit more on a few examples that has engineering backgrounds. All right, so if you recall last class is mainly trying to lay out how we work with MATLAB, right? A lot of these are a little bit more closer to mathematics. So now we'll try to see how we can apply these MATLAB operations to engineering problems. Okay, so this is also the example 2.2 of the textbook. So this is talking about the matrix calculation with scalars. So here, it is trying to let us create a table, a conversion table that we can easily use to convert basically from the pound to Newton. Right? We know that the pound is the imperial, the pound force is imperial unit, right? And at the same time, the standard unit is Newton in terms of the force. So typically, people will refer to a table to do the conversion, right? Or you can also create functions to do the conversion. Okay, so here the scientific data, such as the data collected from wind tunnels, is usually in standard units. However, much of the manufacturing infrastructure in the United States and in the UK as well has been tooled in English units. Right, imperial units. Engineers need to be fluent in both systems and should be especially careful when sharing data with other engineers. Perhaps the most notorious example of unit conversion is the Mars Climate Orbiter, right? So I didn't show it here, which was the second flight of the Mars Surveyor problem. So the spacecraft burned up in the orbits of Mars in September 1999 because of a lookup table embedded in the craft's software. The table, probably generated from wind tunnel testing, used pound force when program expected values in newtons. So you can see that this is indeed a big issue, right? And then in this example, we use MATLAB to create a conversion table of pounds force to Newton force. And the table will start from 0 and go to 1,000 pound force at 100 pound force intervals. The conversion factor is 1 pound force equals 4.44 something Newton, right? So first we need to understand what it means. Right? So we want to create a table, and the table should have what? 2 columns, right? The first column is the pound force, and the second column is Newton. So we want to state the problem, right? The state problem is to, basically the problem wants us to create a table converting from pound force to newtons. The second, we want to talk about introduce input and output, right? The input that we know, the conditions that we know include the starting value of the table is 0 pound force, right? The final value is 1,000. The increment is 100, and the conversion from pound force to Newton is going to be this equation. So the output of this problem is listing of the pound force in newtons. So with all that we have already known, is the programming will be quite simple, right? So basically, we need to create a column of the pound forces, right, from 0 to 1,000. So based on the definition of the column operator that we talked about in our last class, we can easily create this pound force, right, equals 0 to 100 or 1,000, but with 100 interval, right? And the other thing we should notice is that here, since we want to have a table, it's better to have a table that arranged in the vertical direction, right? So the first column being pound force, and second column being the Newton force, right? So then because of that, we need an transpose, a transpose of the pound force. So you can do the same. So another trick when you work on the MATLAB is sometimes if you know a parameter or know a variable that you have already defined, then you can just type 1 or 2 letters and press on tab, right? So the tab is going to give you the, I would say, the recommended parameters or functions that you want to call. So you can see that here, the first one is a pound force, which is the one that we already defined. So it's easier in this way that you don't need to type in everything. You don't type the wrong thing in there, right? So pound force, and the goal is to have this array being transposed, right? So this is pound force. At the same time, we know that we want to have a column of the force in Newton, right? The newtons. So we know that the Newton force is going to be pound force, right? And then multiply by this constant here, right? So maybe before that, we can define this constant. So conversion, we said that for, I would say that the convention for programming in defining the constants are to have all capitalized letters, right? So here, let's just define it as 4.44822216, right? So then we know that Newton force equals pound force multiplied by conversion, right? So this is what we have for the Newton force. So now to combine these two as a table, then we can just do conversion table equals. So combine these two columns. We say that comma or space will put the basically 2 numbers in the same row, right? So then you will have pound force and then Newton force. Right, so this is our conversion table. So if you want to take a look at the table, this is what we have. Okay, so later on, we can actually include more parameters or include more formatting in MATLAB so that we can define basically the first column. And we can even make the title here, the column title here, change it to a pound force. The column title here change to the Newton force. So that will involve the definition of the table in MATLAB. So we're going to talk about that later in this semester. So this is an easy way that we can work on or we can use to create this table here. So you can see the major difference between MATLAB and Excel is that MATLAB uses more programming, right? So you can just type in a command and then you generate all these different types of parameters, right? So basically, if you, for example, want finer definitions, right? So instead of having 100 as an interval, we want to have 1 as an interval, right? So what we can do is easily just change it over here, or even 0.5, right? And then you can do the same, transpose it, and do the calculation, and then you can add the new table, right? So now in this new table here, you have much more columns. And if you just imagine how to create this in Excel, right? In Excel, we said that we could just drag it down, but we have to drag it down all the way to the column or to the row number 2000. Okay, so that's going to be a little bit more cumbersome when you're trying to create this table. But in MATLAB, it's just a matter of typing in the correct interval. Okay, so this is this exact example. So you're going to also have some practice in your homework. So example 2.3, this is talking about the drag force. So I would say this has a more background application, probably in mechanical engineering. But in environmental engineering, we also calculate a lot regarding the drag on air pollutants, right? Especially the particulate matter. So for those of you who have taken the fundamentals of environmental engineering, actually there were different forms of drag forces and drag coefficients. So we'll probably cover that. For those of you who haven't taken that class, we'll go over that when you take the class. Okay, so here this is the second example, calculating the drag. So one performance characteristic that can be determined in a wind tunnel is the drag, right? The drag force basically will try to pull the objects, right, against the direction or relative velocity of the wind and the object, right? So it's going to push the, for example, in the wind tunnel, we fix the aircraft at certain location and then blow wind, right? So the drag is going to push the aircraft along the wind direction. So the friction related to the drag on the Mars Climate Observer caused by the atmosphere of the Mars resulting in the space aircraft burning up during the course corrections, right? So the drag is extremely important in the design of terrestrial aircraft as well. Drag is a force generated as an object, such as an airplane, moves through a fluid. Of course, in the case of a wind tunnel, air moves past a stationary model, but the equations are the same. It's related to the relative velocity. Drag is a complicated force that depends on many factors. So one factor is the skin friction, which is a function of the surface property of the aircraft, the property of the moving fluid, and the flow pattern caused by the shape of the aircraft. So the drag can be calculated by the drag equation, which is this equation. Actually, it's also called the Newton's equation of the drag force. So we'll talk about that later on, well, in other classes, right? So basically, in this form, the drag force is related to the drag coefficient, the air density, the velocity of the aircraft, or the relative velocity between any object and the fluid, and the area, which is a reference area. So if you have a sphere, then that's the cross-section area of the sphere. If you have the shape of an aircraft, then the area will be different, right? There's a specific definition of the area. So although the drag coefficient is not a constant, it can be taken to be constant at low speeds, which is less than 200 miles per hour, which is a pretty high speed, right? So now on the interstate, we normally drive up to 70, 80, right? So this is a very fast speed, which means that we can assume the drag coefficient to be a constant. So suppose the following data were measured in a wind tunnel. You have the drag being 20,000 Newton, the rho, which is the density, This is density of the air. I think this is basically using a much thinner density, right? Because normally in our atmosphere, the density is around 1 kilogram per meter cube. So this is talking about very thin air, right? Potentially in the Mars atmosphere. V is the velocity. This is 100 miles per hour. You need to convert this to meters per second. So basically here, the drag force, you're using standard units, right? So area, density, and drag are all standard units, which means that you have to convert the velocity into meter per second. So calculate the drag coefficient and use this experimentally determined value to predict how much drag will be exerted on aircraft at velocity from 0 mile per hour to 200 mile per hour. Okay, this is quite straightforward, right? So you have the experimental condition, right? You want to calculate the CD first, and then we want to have a range of the velocity and then calculate what is the drag. Okay, so first let's calculate what is the drag, right? So, but before that, we need to define the parameters. So we have drag, right? We can define this as drag experiment, right? Being 20,000. Actually, not without a comma, 20,000. Otherwise, it's going to be two values, right? It's going to be a matrix. So 20,000. And then density, right? Density equals 1e minus 6. Okay, so one thing we need to pay attention to is the MATLAB doesn't recognize units, right? So we have to know all the units by ourselves, right? So that's why a lot of times when people create codes or scripts to do the calculation, they would comment on the unit for each of the parameters. So you have density, you have area equals 1, right? So now it's the velocity. So this is 100 mile per hour. We need to convert mile per hour into meter per second. So let's search for 1 mile per mph2 meter per second. Okay, so you see 1 mile per hour is 0.44704 meter per second, right? So you can just do V experiment is actually 100 multiplied by this constant. Okay, so you have the velocity during the experiment. So now we can calculate the drag coefficient. So CD, right? CD equals drag multiplied by 2 divided by density divided by velocity square divided by A. Right? This is trying to inverse, trying to find out the CD, right? Divide by all of these parameters correctly. Okay, so we can find out, oh, basically we didn't define drag here. We used drag experiment in the beginning. So we'll do experiment. Okay, we didn't define A either. Use A area. Okay, so this is a CD. Okay, basically you have the Newton here, and you divide that by the velocity, right, which is around 44 meter per second. Okay, and then you divide by the density, and then you divide that by the area. Okay, the CD looks a little bit high here, but it's okay, right? So then we have the CD. It wants us to determine the value and predict how much drag will be exerted on the aircraft at velocity from 0 to 200 mile per hour. Okay, so we can do the same thing, which is to create this table, right? So we can see velocity, say V table, and define it as 0 to with 10 mile per hour as the gap. This is a V table. It has this one row structure. We can just do the transpose. Okay, so you have this array, this column of the velocity. Now we just need to calculate the drag. So drag table will be equal to CD multiplied by density multiplied by V squared, V table. Remember, do we directly do the square over here? No, we want to do a point by point or element by element square. Okay, so if it's element by element square, you would add a dot operator here. Okay, multiply by area and divide by 2. Okay, so this is the drag equation or the drag values. So now with both of these together, we can do the conversion table. One thing that we made the mistake in this table is, well, here you're trying to create this column with a mile per hour, right? So remember, in this equation here, we have to use the meter per second. Okay, so instead of having the drag table being this way, right, we need to do the conversion. So it's going to be V table multiplied by what? Multiplied by that conversion value, right? So if you scroll up, so it will be this value, 0.44704. Okay, so this is the right way. So now if you look at this table, okay, so when velocity is 0, we have 0 drag. When velocity is 100 miles per hour, then let's see again. Drag table. So we have to use the conversion table, right? So if you go to the conversion table now, so this is what the problem provided us with, right? 100 miles per hour, you have 20,000 Newton, right? So when it's 200 miles per hour, you have 80,000 Newton, right? So this is basically the programming here. Again, you can see that we made a mistake here because we did not convert the velocity from mile per hour to meter per second, right? So we have to bear in mind that the correct unit has to be used. So this is basically the scripts that you can type into the MATLAB, although we typed in already over here, right? So you can just type in again. So see clear, CLC, and then you can copy and paste. So this is a table. All right, so inside the table here, you can take a look again. This is velocity, right? Velocity 100 miles per hour in meter per second, right? So the value is 20,000. Of course, I think the problem wants us to have the conversion based on mile per hour, right? So either way is good as long as you clearly states what your answer means, right? So this is script. So then we can continue with a little bit more about the formatting of the number here. So you can see that some of the numbers is directly provided with the values, right? 20,000 is an integer. Some of them have extra zeros, right? Some of them are shown in the scientific way and so on. So you may wonder, well, what is the general rule of thumb for MATLAB to show all of these values? For example, if you type in, let's say A equals 1, then A is going to show as 1. But what if A equals 1.5? Right, it's going to show as 1.5000. So it looks like there are some inconsistency here in showing values of different, showing different values, right? So basically, you can control how the values look like or how the format is for different types of values. So for example, when you type in Avogadro number, Avogadro's constant, right? So instead of, made a mistake here by typing in the prime here because prime is not allowed, right? So this is Avogadro constant. And you can see that it actually provided 4 numbers after the decimal point, 4 digits after the decimal point, right? So you can also type in these here. It's a similar thing. You have 4 digits after the decimal point, right? If you type in this value here, it's the same thing. If you type in A equals 51.1, you're also going to have 4 digits after the decimal point. So this is a default format for all of these numbers, right? So basically, when it's an integer, then you show as an integer. When it's not an integer, when it has decimal point, the MATLAB right now in the current format actually it's only going to show you 4 digits after the decimal point. You can of course change the format. You can change it to format long. You just need to type in here. So basically, I'm typing again, format long. So now if you type in A here, you can see that it goes all the way to the end. And it happens to be that the last digit is 1 here. Okay, so this is actually related to the machine's accuracy. It's a rounding off error, right? So a lot of the calculations in MATLAB are based on the approximations. It's just that it has a high precision, right? But it doesn't mean that it doesn't have error. So the reason why we show the value here is only because you can ignore the rounding off error, right, in the computational tools. And this is the common feature or common property for all of these computational tools. It is not like pencil and paper calculation where you know the exact value. So for any calculation that involves computer or machines, there's always a truncation error, a rounding off error. Okay, so you can also change the format to short. So let's just type in here, short, and then define A again, right? So this is sort of the default definition, right? So now if we define A as 1, it's just showing you the value as 1. So there are also a little bit more sophisticated or a strange type of format. So for example, you can have format plus, right? If it's format plus, then if you type in A is going to be plus, right? So as you can tell, it's going to tell you what is a sign in front of for the value. Okay, so for example, if you define this iron diameter, then the iron diameter is plus, sort of converting it into a binary results, right? But it's only giving you 1 or 0. Is it positive or negative? So here it shows you all the number display formats that is available in MATLAB. You can have the format short, which is sort of the default format. You can have the format long, which give you the 14 decimal digits. Format E, which is scientific way of showing the values. Is everything is going to carry the E here. It's sort of like the mode that you can choose on your calculator, right? Format bank, right? Format bank is only 2 decimal points. Only the real values are displayed. Basically, you ignore the imaginary part of the value. Format short engineering, format long engineering, plus minus, so on and so forth. Okay, so basically, it's the all different types of formats you can use for the number display. Okay, so this is the next example. As we mentioned, we're going to focus on a few examples in this class. So the Voyager, it's about the Voyager, right? So it's the man-made aircraft that has traveled the longest in our solar system right now. Okay, so the Voyager 1 and Voyager 2 spacecraft explore outer solar system during the last quarter of the 20th century. It looks like this. Voyager 1 encountered both Jupiter and Saturn. Voyager 2 not only encountered these 2 planets, but also continued to Uranus and Neptune. So during the encounter, they can get accelerated and travel even faster, right? So it's like a bow that shoot these aircrafts even, or spacecrafts even faster. The Voyager program was enormously successful and continued to gather information as it leave the solar system. The power generation, which is a radioactive material, are expected to function until at least 2020. Right. So I think recently there are some news about the Voyager sending some images back to the Earth, right? Although the functions of the machines are starting to die down. The power source is a sample of plutonium-238, which as it decays generates heat that can produce electricity. So at the launch of each spacecraft, the generator produced around 470 watts of power, and because of decaying, the production had decreased to 335 and almost 20 years after the launch. The power is used to operate the scientific package, but if it were diverted to propulsion, how much of acceleration would you produce in the aircraft or the spacecraft? So the Voyager 1 is currently traveling at the velocity of 3.5 AU. So the AU is an astronomical unit, right? So Voyager 2 is at 3.15 AU per year. Each spacecraft weighs 721.9 kilograms. So state the problem, right? You want us to find out the acceleration that is created by the power, right? So you have the power. So let's just try to type out the equation here. So we know that the power is equal to force multiplied by velocity, right? So you have the watts here. So if you know the force, then if you know the force and if you know the velocity, right? So you can basically make this equation work, right? So further, the force, we know it's actually acceleration multiplied by the mass, right? And then multiplied by velocity. So here, the problem basically wants us to solve what is the A, right? So A should be equal to P divided by M divided by V. Okay, so we're trying to find out what is acceleration, right? The P is already provided, it's 335. So the M is also provided, 721. And then the V here, we just need to properly convert all of the velocity into the AU units into meter per second. Okay, so then you can find out basically what is the AU. AU to meter. So it's 1.4, almost 1.5 multiplied by 10 to the 11th meter, right? So we can define this conversion constant as this value, right? One thing we forgot is format, short. Conversion constant is this value. And then we should convert the velocity into meter per second, right? So we can define V1, right, which is Voyager 1. It's just called V1, Voyager 1, is what? 3.5 multiplied by this conversion constant, right? And then this is velocity per year. We want to convert it to per second. So you divide that by 365 days, and then divide by 24 hours, and divide that by 3,600 seconds per hour, right? So this is the Voyager 1's velocity in meter per second. You can also do the same for Voyager 2, which is 3.15, right? So this is velocity for the Voyager 2. So you can see that they're now traveling at around 16 or 15 kilometer per second, right? Which is very, very fast. So for our cars, we say that 100 miles per hour is 44 meters per second, right? But these spacecrafts are traveling at 16 or 15 kilometers per second, right? Which is very fast. Okay, so now you have the velocity, right? So we just need to solve for the acceleration. So the acceleration for Voyager 1 is 335 divided by mass, which is 721.9. So we should define the mass too. So mass equal to 721.9, right? So I had this semicolon here, so I can hide the output. So, but you can also show the output here. You just confirm that you type in the right value. So then you can calculate the A here. AV1 equals P. Oh, well, we didn't define P either. So P is 335. AV1 equals P divided by M divided by V, V1. Right? A, V2 equals B divided by M divided by V, V2. Okay, so these are the accelerations. You can see that acceleration is very, very small here. So that's why these power are not used to accelerate the Voyagers, right? So they're used to initially guide the Voyagers into um, their orbit, and then you use the planets or you use the sun to accelerate it, right? So then you can sort of like a bow effect that shoots the Voyagers away from the sun. Okay, so you can do that separately, like what I did here, but you can also define the velocity as an array, right? And then do the calculation. So basically, if you just copy what we have here, right? And then copy and paste, and then you can see these are the values that we calculated. It's similar to what we had earlier. Okay. So then you can see that, well, you can type in a lot of the values, right? So if you just copy and paste what we created earlier with our own code, right? This is our own code. So to do the comparison, right? This is a code that I just copied from here. Acceleration 1 is 2.78 e to minus 5. The other is 3.1 e to minus 5. And this is what we have here. They're the same, right? So, and also, you see that this is our code that we just created. So then we may have the question, well, we just wrote this code, right? And we don't want to copy it every time, copy and paste every time if we want to go back, right? So for example, we just created this calculation here. Maybe 1 month later, we want to come back. We don't want to scroll all the way up to the command history and copy them out. So is there a way to save our scripts, right? Is there a way to save our parameters also, right? So then this is about the saving of your work, okay? So first, regarding the commands that you type in the command window, it is quite easy to do it. So the only thing is that you have to remember to record your commands before you type in. So what you can do is you can just type in diary, right? Or type in diary on, and then you can copy whatever function or scripts that you type in. For example, you type in here and then did all the calculation. And then here, you just type in diary again. So you basically stopped recording. So now you can open it. You can try to open it just with a notepad. And you see that this is what you have already typed in your command window, excuse me. So this is what you have typed in. So you can see that this is what you have typed in your command window. Okay, so this is one way to save your commands, but a lot of times you actually don't need your commands to be saved here. But of course, you can go to your notepad or go to your Word document, copy and paste everything here. But is there a way to directly save it in MATLAB, right? Is there ways to save everything more easily, okay? So this is about the commands. And then before talking about saving all of these commands in the more easy way or more widely accepted way, you may also want to save your workspace, right? You spend a lot of time calculating all of these variables, and you may want to save these variables. So what you can do is you just type in the command save workspace. So now you see in the folder here, you have this workspace.mat, right? So you can just drag it in to the MATLAB command window, right? So for example, we can CLC clear our memory, right? Everything off. And then you go back, drag it in. Basically, the command is load workspace.mat. And you can see that our values are back, right? Our variables are back in the workspace. And so you can keep working with your workspace. or you can type in, right? So clear your memory instead of dragging. For example, if you're working with computers without a mouse, or you're working with an online version of the MATLAB, so sometimes you may be limited regarding dragging action. So then you can type in load, right? Workspace, just make sure that the file name you typed in is correct. Okay, so then you can load all your variables you just defined over here. So then it said that we could save the command as the diary, we can save the workspace, but a lot of times, I mean, even for the variables here, we're not that very interested, because theoretically, if you have all of these commands here, they would generate the same variables, right? So instead of saving as a diary, or is there even easier way, even more convenient way to save all of the commands? And there is. So the recommended way to save your commands is actually by creating the M files. So I put highly recommended here, which is basically you're going to work on your homework problems from now on using the M files. Right? You have to save your scripts so that I can take a look at it, or the TA can take a look at it, and then they can run it. Right? Everyone, or your colleagues, your friends can run it. Okay. So the way to create an M file is to just click on the new script, right? So click it, right? Now you have an editor, right? So now you see that we have a new window here. So this is actually the script window, okay? The script editor. So you can, again, go back to what you had over here, okay? And then you can save it. So Control F, or just click the save. So we talk about the current directory in our first class, or in our second class, right? When we first introduced MATLAB. So the file will be saved to the default current directory. You can name it just as, for example, we're talking about the example problem, right? Example 2.4. You can name it as example 2_4. So you can't use .4 mainly because there's a conflict with the .m, right? So the script files has a extension of .m. So if you have a dot here, then it's going to recognize as .4.m. Okay, so avoid using dot in your file name. So just save it like this. Okay, so now you can see in your current directory, there is this example 2-4. So then you have this script over here, right? So then how do we run it? Of course, you can copy and paste and then run everything here. But an even more easier way is to click the run button, okay? So you just run it over here. Okay, so here, CLC, just run it, and then it's going to give you the values that you just calculated, okay? So you can see that didn't give you the mass or the power, the velocity, mainly because they have the semicolon here, which is suppressing the output, right? So the output that you want to show are the velocity and the acceleration, because there are no semicolons here. So you can add a semicolon here, and then it's only going to show you the acceleration, right? So, or you can remove the semicolons here. It's going to give you everything. And another convenient way for, or another, I would say, advantage for using the M file is that now you can type in all the comments that you want to add into the problem. Okay, so for example, this is example 2.4, because we said that everything after this percentage sign is not read by the MATLAB. This is only for your personal reference, or for your colleagues' reference, right? So in this way, it can give you much better idea about what you are typing about, right? So talking about having a good habit for coding, this is good habit, right? You have a annotation for each line of your code. So in the future, let's say 1 month later, you're trying to look at this problem again, you can easily catch up based on what you have commented over here. Okay. Another advantage for using the M file is that if you want to run it with different values. For example, now you're trying to look at the velocity, trying to put in another velocity, or to, let's say, to put another mass, right? Instead of 721, let's say we reduce it to 600. Then you can just easily change it over here and then click run. It's going to give you new values directly, right? So you don't need to go back to the command history to select all the commands you already typed in to run the code, and it's automatically saved in your folder. Okay, so you can always come back and refer to these to find out what you have typed in. Okay, so this is about the saving, the scripts, right? So it's very convenient for editing, saving, and reusing, right? So it can also avoid conflict of variables among tasks, because it could be that you work on example 2.3, 2.4, and both of them have a variable called A. And then these two variables, although it's having the same name, have different values. If they have different values, you cannot easily, I mean, there will be an issue of overriding. You may get different results or the wrong answers, right? So in this way, if you create a separate file, right? So this is a file that I just created, right? This is, again, going back to the drag problem, right? So these two are not going to interfere with each other, okay? So if you run this one, even if you have the same value, let's say we type in A equals 10, right? So for example, if this is the output, right? And this one has A equals 100. Okay, so if you run the first function, let's just hide some of the outputs over here. All right, so after you run it, you have the A value of 100, and after you run this one, you have the A value of 10. These two are not going to interfere with each other. But if you run these together, right? So in the command window, then the things is going to be different, right? Because they're going to override each other, and then they could interfere with the final answer that you want to get, right? Another thing we want to mention is that, well, you can create different problems or different M files for different problems. But for example, if you want to create a file for all of the problems in one chapter, right? So because a lot of these problems are simple problems, so you can include everything in one file, right? If you want to do that, an easier way to to tell functions apart. For example, now let's do CLC clear, right? And then let's do example problems in chapter 2. So now I will try to save this M file and then name it as chapter 2. Okay. So we just did 2.3. We can do it over here. Copy, paste. All right, we just did 2.4. Copy, paste over here. Let's delete the A values. Okay. So if you want to, let's say, as you accumulate problem 2.3. So as you accumulate more and more of these problems, 2.3, 2.4, 5, all the way to 2.100, if you want to easily go to certain section of the code, so one way to do that is you can just Control F and then try to find. For example, here you can do 2.3, and then it's going to directly guide you over there. Another way you can sort of simplify your code is you can use the double percentile sign here. Okay, so if you double it, so you can see that now you basically create a new section, right? So before I type in the double percentile sign, you can see everything is below this blue line here. But once I type in and click space, so now I sort of have a new section. And then to go to certain section, you just need to click the down arrow of go to, and now you can see they even include the titles of these different problems, right? Go to section problem 2.3, problem 2.5. So it's easier for you to go over all the codes that you generated within this one big file here. Okay, so basically the double percentile sign creates the sections. Okay, so as a summary, editors and M files, right? We introduced this new tab here. This is not existing in our first MATLAB class, right? We said that there were several panels, but now I have to say that from now on, you will actually work more with the M file in your programming. Okay, so command window will just be used as sort of like a display from now on, or you can debug, right, to correct your code, trying to find the problems in your code. Okay, so the M file in MATLAB is analogous to a text file in Microsoft Notepad. Right? An M file is created in the MATLAB text editor. In the M files, you can save your programs, a list of executable commands as M files. You can reopen and modify your program. Very useful for debugging, correcting errors as you develop your programs. As we go to more sophisticated programs, right? So comment in the programs. Every time you write a program to be saved, it's helpful for you to comment, right? So just like what we did over here. To insert a comment on the line in the editor or in the command window, just use the comment operator, percentile, percentage sign, and then the MATLAB will not run the lines that begin with the comment operator, okay? So it's basically the editor comments will appear in green, right? The green ones will not be red. It's only for your personal reference or someone else's reference. The comments allow you to, or others to more easily understand your program. And when your lines of code are easy to understand, your code will be easier to use in the future. Okay. So again, now we're talking about the art of writing of the well-written code, right? So talking about convention or having a good habit of coding. So a well-written program is like literature. It contains comments that explains what your program requires as input, what are the variables in the program, what your program computes and displays. It's useful for you to add a set of header comments that include the name of the program, your name also, right? The date of the program was created or modified. So for example, here, okay, say created by Wang, and then August 8th, 2025, right? Lincoln University of Miami. Okay, so basically, whenever you come back and then you start to realize, I mean, you're creating this library of code that you can use in the future, right? So this is going to be very convenient as you accumulate your code, your functions. So we'll talk about functions in the future. Accumulate all of these codes together, and then you can build upon your repository, build on your literature, and can do more sophisticated problems. So I recommend you to use MATLAB in others of your classes as well, right? So you're also taking physics, chemistry, or taking now some of the engineering classes. Try to use MATLAB, right? Try to solve your problems using these scripts or codes. It's much easier to keep the hard copies or these electronic copies of your answers, right? And it's much easier to share with the others. And if you have problems, you can always come back to refer to them. Right? It's a much cleaner way to work on your homeworks or to solve problems. Okay, so save code in the M file. You can open the editor by basically you can just create new over here, right? So enter the command edit. Let me try. Not sure if we can do that, but let's do edit. Yeah, indeed, you basically create an editor here, but you can also just click new script or new to create the new M file. So now you can enter the code lines of codes, and after you type in the code, you can save it, right? So as I said, it's very convenient for editing, saving, and reusing. So you can also avoid the conflict of variables among different tasks. So once you have the code here, you can run it by just clicking the run, or you can also press F5 So F5 will also run the code. Okay, so as a summary for this class, I think we talked about, let's see, the number display format. So in the beginning, we did a few example problems manipulating the arrays or matrices. We talked about the display format of the numbers, right? The long format, short format, plus format, or so on, right? So it depends on your need, of course. And then we talk about saving our work, either using command, right? Basically the work in command window or the workspace, but more importantly, is saving the commands or saving our scripts in M5. Just typing it in M5, okay, which is highly recommended way. Okay, so I would say that from now on, in all of your future homeworks, now when you submit the homework, please submit the M file. Okay, so with the M file, it's easier for us to run, to comment, and then it's also easier for you to keep a record of your work. Okay, so that's it for this class. Let me know if you have any questions. Thank you.